Hello, so today I'm going to be talking about some of the properties of logarithms. In a previous video, we've looked at this property and this property, but there are a few other ones that prove to be useful when solving these sorts of equations. So the first one is, if you have a logarithm where the two inside terms are being multiplied together, you can take those out as log b of u plus the log b of v. So when you're multiplying two expressions inside of a logarithm, the multiplication becomes a plus when you try to separate them. The second property is if you have a logarithm where the two terms inside are being divided by each other, right? Those come out in a similar way where the top one is what your first term is, and then instead of adding, because you're dividing, you subtract the bottom one. And then the third property that we're going to look at is if you have a logarithm where you are raising something to a certain power, right? That comes out as, right? So you take the power and that ends up multiplying the whole expression. So the main things are, if you have two terms being multiplied, you end up with two adding logarithms. If you have two terms being divided, those end up separating as two subtracting logarithms. And if you have a expression being raised to a power, that power becomes a multiplier to the entire logarithm. So now I'm going to go through some examples of how these work out. So the first example I'm going to look at is log base 2 of 4x is equal to 5. So we know that we can pull these two apart by going log base 2 4 plus, right? That becomes a plus of log base 2 of x is equal to 5. You might be able to do this in your head, but just to get some practice of the change of base theorem, we can go the natural log of 4 divided by the natural log of 2 is going to give us 2. So we can say that this value is 2. We can keep the log base 2 of x equals to 5, right? So we can just subtract the 2's out. We can go log base 2 of x, 5, 4, 3. So 2 to the 3 is equal to x. So x is equal to 2 to the 3, just by definition of what a logarithm is. Or x is equal to 8. The next example I'm going to look at is log base 4 to the 2x squared is equal to 3. So we can take this squared, put it outside the logarithm, and say 2 log base 4 of x is equal to 3. We can say that log base 4 of x is equal to 3 over 2, right? Because we can just divide 2 from both sides. If we raise 4 to the power of both sides, these end up canceling out. X is equal to 4 to the 3 halves. What's 4 to the 3 over 2? It's 8. So that ends up being 8. So in this example, just looking at it, it seems that it might be helpful to condense this up using the properties we've learned. So first thing I'm going to do is take this 3, right, and make it an exponent. Just take the 3, put it up with the 5. So then we end up with 5 to the 3rd is 125. So I'm going to take, just to clean it up a little bit, I'm going to go log base 4. 5 to the 3rd is 125. 5. And since this is a subtraction sign, I'm going to condense these two by division, right? So that becomes x over 125. I'm going to raise 4 to the power of both sides. These end up canceling out. I get x over 125 is equal to 4 to the 5th. 4 to the 5th is 1024. And I can say, I can multiply both sides by 125. So we end up with x is equal to, that big number. 128,000. So this one didn't end up being very nice, but it still works. So at this point of the video, I'm just going to go through how we can reason that these properties actually work. So if we have log base b of uv, so what I'm going to do is I'm going to say that u is equal to b to the x and v is equal to b to the y. Why is u equal to b to the x? Because I'm saying that there exists somewhere out in the world some number that makes this expression true. I don't know what x is, but it's out there. It might be irrational, it might be whatever, but it's out there. So what I'm going to do is substitute. So I'm going to say log base b of b to the x times b to the y, log base b. When you are multiplying things like this, you could say bx plus y, log base b, and then this is base b, so we can cancel these out and just say this is equal to x plus y. What is x and y? Well, we have to go back up here. So if u is equal to b to the x, we can say log base b of u is equal to x. And if v is equal to b to the y, we can say log base b of v is equal to y. So what's x? X is log base b of u. What's y? Y is log base b of v. And so then we end up with the expression that we were given. Log base b of u plus log base b of v is equal to log base b of uv. So the next property we're going to look at is log base b of u to the v. So we're going to do the same thing we did last time. So I'm going to say there exists some number x such that u is equal to bx. I don't know what x is, but it's out there. We can say log base b, and then I'm going to substitute b to the x for u. This turns into b to the xv, right, because I'm just multiplying these. We have a log base b into b, so we can say this is just xv. What's v? Oh, sorry. What's x? Well, you have to go back up to here. X would be log base b to the u is equal to x, and that's just the definition of a logarithm. So x is log base b to the u. And that is what we have written down. Since we've already shown the other two, this one sort of just comes out of those. So we can say log base b of u over v, right? So this is the same as saying log base b of u times v to the negative 1, because the negative 1 just means it goes onto the bottom of the fraction. Since these are being multiplied, log base b of u plus log base b of v to the negative 1, right? And then from the previous property, log base b of u, and then we can take this negative 1 and put it out here. So minus log base b of v. So that's all I really have to say about logarithm properties. Stay safe, good luck studying, and wash your hands.